So I'm Toma Aquino. I'm a postdoc in Barcelona with Marco Dents, and we work on upscaling transport from the port to the Darcy scale with theoretical models such as the continuous time random walk and the time domain random walk. So what I have here today is a work on using the time domain random walk to create an efficient model for conservative transport in media where you have broadly distributed transport properties in space. Okay, so you have something like this. Currently we are using a 1D model as a proof of concept, let's say. And you have regions where transport properties vary slowly, and we assume they are constant. But these regions can vary quite broadly in size. Okay? So the problem with the traditional techniques, whether they be Lagrangian or Eulerian, is that it takes a long time to run these simulations because you are overly resolving, let's say, these areas where the transport properties stay constant. And so that should be a more efficient way to do this. Okay, so we consider two different kinds of transport processes in this type of medium, where the direction and diffusion are controlled by trapping, which is taken care of by this retention coefficient here. And we use regular dispersion and dispersive trapping. Okay? And then again, like I said, we consider a broad distribution of these regions and also a broad distribution of this retention coefficient. Okay? So then what we do is we set up the problem as a time domain random walk, where we consider that particles, so solid particles, which represent mass of the solid, make jumps between the nodes, so the interfaces between these regions of different properties. So that's what I'm saying here. At each step of our model or approach, let's say, we jump with a length that is according to the size of the region, whether to the right or to the left, with a certain probability. And then what we need to do is quantify the statistics of the time that it takes to do these jumps, so that our time domain random walk is equivalent to a regular model for transport in this kind of medium. Okay, and then we would like to compare this to a traditional Lagrangian model, and we use a classical Langevin formulation for that. So what we can do is we can consider the properties of transport in these regions we call unit cells, which are basically the two regions around the place where the particle is located. And then we find the statistics of the transition of the particle to the right or left and how long it takes. Okay, so we do this with the Green's function method, and we can check that our results for the waiting times and the transition probabilities agree with the detailed simulations. So both here I'm showing you the fluxes, so the waiting times to the right and to the left, and here I'm showing the probabilities of transitioning to the left or the right for the two transport processes that I discussed before, as a function of the relative size of the two regions. Okay? And then we also showed that we can use different approximations for the waiting times, which allow us to make the model more efficient. Okay, once we do this, this is very efficient. So for the case that we checked for pure trapping with no advection, it was about 1,000 times faster than a traditional model. And we can write equations for this coarse-grained probability of being at the interfaces. So then we developed the methodology to actually reconstruct the full concentration profile, including the regions where the properties stay constant. And we can do this also quite efficiently, and we still get about a 500-time speed up in our simulations. So as you can see here, we can capture very well the concentration over space. So this is an example, like I said, for a problem where we have no advection but only dispersive trapping, or trapping, sorry. And using our coarse-grained model, let's say, we can also capture the variance of the plume averaged over different realizations of this medium. So just to conclude, at the moment we are working on generalizing this to higher dimensions. And one thing that we think has a lot of potential for this type of efficient model would be to apply it to discrete fracture networks, no? Or fracture networks in general, where we would generalize our concept of a unit cell to take into account different fractures um, coming out of different nodes.